What's up, guys? Finally getting to this video breaking down motor calculations and all the steps. I had made an earlier video that kind of listed all the steps, but I kind of waited too long, so I'm going to kind of go over all that now. So let's dive in. Here's our question. Not quite in question form, but I'll go ahead and break it down for you. We have two motors on the same feeder with copper conductors. We have 75 degrees Celsius terminations. One of our motors is 115 volt, 10 horsepower, and the other is 115 volt, 7.5 horsepower. And throughout this, we're going to size the overload protection, the branch circuit conductors, the branch circuit overload protection, the feeder conductors, and the feeder overcurrent protection. Step one is very simple. You're going to go to table 430.248 for full load current in amperes for single phase alternating current motors. As you can see, the 115 volt column down at the bottom, we have 100 amps for 10 horsepower and 80 amps for 7.5 horsepower. Now, just for simplicity, you're never going to use the FLA. There are times, but for this basic calculation, you're always going to use the FLC. FLA is going to be full load amperes, and FLC is full load current. Same thing. One way to remember it is FLC is code book, FLA is actual or what is listed on the equipment. But for purposes of calculation, you're always going to use the FLC unless I tell you to. Here is that table, 430.32A1, separate overload device, and it's going to give you some circumstances. Our question did not come with a marked service factor. Our question did not come with a marked temperature rise of 40 degrees Celsius or less. We fall under the category all other motors. So we'll be taking our FLC and multiplying it by 115%. As you can see on this sheet over here where I got it all written down, we went to 430.32A1, all other motors, 80 amp FLC times 1.15 is 92 amps, 100 amp FLC times 1.15 is 115 amps. Now, from there, you would go to 240.6A for your regular sized overcurrent protected devices, your standard sizes. It may be a fuse, it may be a circuit breaker. In this instance, it's going to be a setting, so just keep those numbers in mind, 92 amps and 115. Now, one thing to remember when you are sizing overloads is that the next size up rule from 220.5 does not apply. You're going to round down when sizing overloads, down to the nearest size overcurrent protected device rather than up, or it may just be a setting. As we continue on, step 3 is going to be size of branch circuit conductors. 430.22. Now, to do that, you're going to take the FLCs, full load currents, at 125%. So the FLCs are 7.5 horsepower, 80 amp FLC times 125% is 100 amps. 10 horsepower motor with 100 amp FLC times 125% is 125 amps. Fairly simple. Now, you're going to go to 310.16 to size your wires. The next size up rule does apply when sizing the conductors. And if you go over to 310.16 in the 75 degrees Celsius column and find your amperages to match them up, you're going to come up with these. A number 3 copper AWG and a number 1 copper AWG. Step 4 is going to be sizing branch circuit, overcurrent protection, short circuit, and ground fault protective devices. Now, in our calculation, we're using an inverse time circuit breaker. So we're going to use our FLC 7.5 horsepower. We're going to go to 430.52, which I do want to show you guys. This is that table, and you can see single phase motors. Inverse time breaker is a 250% multiplier. And as I'm sure you're aware, some of these figures are going to seem very wild. I'm sure you've run into AC units where you have a 14 amp wire on a 30 amp breaker. This is going to be along those lines. This is going to be exactly that. So then here's our math. We took our 80 amp FLC multiplied by 250% and got 200 amps. We got a 10 horsepower motor, 100 amp FLC times 250% and got a 250 amp breaker. Traditionally, you're going to go to, again, 240.6A. The next size up rule does apply, But in our case, we're lucky. There is an exactly sized 200 amp breaker and an exact size 250 amp breaker. And that's what we're going to be using. So next is step 5. We're going to go to article 430.24 and we're going to size the feeder conductor. You're basically going to see that table and it's going to say single motor and you're just going to size it accordingly. So you're basically going to take the largest motor FLC times 125% plus the sum of the remaining motor FLCs. So our largest motor was 100 amp FLC times 125% is 125 amps. Plus 80 amps, which is the remaining FLCs left in this equation. Add them together and we're going to get 205 amps. Then you're going to go to 310.16. And again, the next size up rule does apply when sizing the conductor. And you'll see in 310.16 in the 75 degrees Celsius column, a 4/0 copper AWG wire is going to suffice us. And then lastly, we're going to size the feeder over current protection. And that's in 430.62. And to do that, if you go to that article, it's going to tell you to take the largest branch circuit over current protective device plus the sum of all the remaining motors FLCs. It's easy to get confused here. So in our calculation, we have a 250 amp breaker, that's the largest branch circuit protective device, plus the remaining motor FLC, which is 80 amps. We're going to add them together. That gives us 330 amps. Then once again, we go to 240.6a and select the circuit breaker. Next size up is going to be a 350 amp breaker. And then just to break down our whole calculation, that was it. This is just a review. Step 1, found the FLCs, 80 amp and 100 amp. Step 2, found the overload, sized them, 92 amp and 115. Step 3, we sized the branch circuit conductors, a number 3 AWG copper and a number 1 AWG copper. Step 4, we found the breaker for the branch circuit, 200 amp and a 250 amp inverse time circuit breaker. Step 5, we sized the feeder for the whole entire circuit, which is a 4/0 AWG copper, 75 degrees Celsius. And step 6, we sized the overcurrent protection for that feeder, which is a 350 amp breaker. Now, this is just a standard for a simple form calculation. There could be all kind of oddballs thrown in there, intermittent duty, periodic duty, stuff like that, where you're not going to use the 125%. There's going to be actual instances where you do use the FLA, like I just mentioned, when you have an intermittent duty or periodic duty motor calculation. But this is just a general, overall, simplistic way to size several motors. And even to save a whole nother video, if we were sizing one motor, we would basically just use steps 1 through 4. So I hope that helps. If anybody has any questions or wants me to specifically focus on anything else, let me know. I do offer one-on-one tutoring through Zoom or any available platform. It's really cheap. I'm just not really after the money. I'm just trying to help some guys. I've done it with a couple of guys on here, and it helps me. So there's no better feeling to me than to help you guys. Like, share, follow with your favorite family, friend, electrician. Let me know how I did. And let me know what you guys want to see. I'm trying to cover as much as I can on here. Like, share, follow. Thanks.